Hello my friends, welcome again to my video channel. Today in part 2 of the project with the Subtone encoder for the Braun SE400, we will first check whether the simulation we have done at the end of part 1 is correct, whether the result is correct. So we will replace the 1 microfarad capacitor by 10 nanofarad. Let's start. The 10 nanofarad capacitor is in, and for the second oscillator I did the same modification: 1K to ground, 10 nanofarad, 100K in series to the cathode. To the cathode of the other cap diode, so both oscillators 10.1 and 10.7 megahertz are connected now, and I can install the shield and do the next test. And now the same test setup as we had before. AF generator, that's the input to the modulation, that's the FM deviation meter, that's the high frequency, and this output is connected to the scope. And for a more stable picture, the scope is triggered externally by the trigger output of the generator. Full scale is 1.5 kilohertz. I cannot use the best resolution with 500 hertz, there's a little bit too much noise in the system. I think this one is a bad guy. This modulation meter is a little bit noisy. 500 at 250 hertz would be there. Frequency is 40 hertz. I increase the voltage up to 250 hertz deviation. We see the signal, and when I increase the frequency, we now have a rather stable 100 hertz. Feels the same. I go to the next decade. This is now 1 kilohertz. A little bit too much for this purpose. I go down to 290, 270. That's the maximum. The maximum frequency of the CT-CSS system is 250 hertz. So we are here at 250, but we have still the same deviation, nearly no difference. I go back to down to 180, 140. When I go to 100, back to 100 hertz where we came from, we have the same deviation as before. And now we'll swap over to the other modulator. I switch to FM repeater operation and connect it on this point, and we can see there's a little bit more. I think I have to restart the system. One moment. Yes, it's a better lock. The lock here is better. Maybe it was a lock on one of the harmonics. We still have the same deviation at 100 hertz. When you go up to 250, no difference. When I go down to very low frequency, 28 hertz, okay, this is too low. But when I increase it to 50, 60, we have the same deviation. So I can say now the problem is solved. We have a linear deviation, not influenced from the frequency, not depending upon the modulation frequency, and both oscillators have the same sensitivity. So we can have a look at the final schematic. This is the final solution we can realize now. We have the 100K and 10 nanofarad in series directly connected to the cathode of the varicap. 1K to ground. 1 nanofarad feed-through capacitor. I will add a second 1K in series to reduce the sensitivity. Same for the second oscillator, 1K 10 nanofarad, 1 nano feed through, 1K to ground, also 1K in series. So we have here 2K, we have here 2K in parallel. So the impedance here we expect is 1K, set is 1K, and the necessary modulation amplitude will be 1.4 volt RMS. I've measured 630, 650 millivolt RMS at this point. So we need here the double voltage. This is 1.4 RMS for 250 hertz deviation. These two inputs are connected in parallel, and the signal will be fed in via this 5-pole plug. Pin 2 and 3 is the input, 2 is input, 3 is ground. I use here additionally ferrite beads against high frequency. Here 10 nanofarad for ground, also against high frequency, shielded cable of course. Here we have the power supply, 14 volt internal, it is 15 or 16 volt, 200 milliamp fuse connected to pin 4. Here's a PTT from the microphone connector. I need PTT information for the Subtone encoder. It's necessary to have this information to switch on the Subtone in transmit case only. And also important, as I've seen, the encoder I have needs switching on and off via PTT line to take over a new frequency, a new set frequency. There's a digital unit based on a PIC, so it's necessary to switch it on and off. So we need a PTT, and when we are in receive mode we can use another subtone, and then when PTT comes the new subtone is written into the system. That's a complete circuit which we can realize now. The work is done. We have here the additional 2 resistors, external resistors to the in-feed, to the feed-through capacitors. I've chosen here 2 capacitors in parallel as a fixed point. Each has 3.9 nanofarads. Totally they have nearly 10 nanofarad, so it's not important. Small deviation. Here we have a shielded cable, and the shielded cable goes to the connector. The connector on the rear side is this one. Here we have the cable from the modulators, 2 ferrite beads, and here you see nothing, but now you can see it. This is a 5-pole plug or connector, not the plug, the connector. I drilled a separate hole in it. And here is the feed through to the lower side of the chassis. We have the connection to the microphone, to the PTT connection, and to the power supply. Here we have the feed through. The white wire here is a connection to the PTT of the microphone connector, which is this one, and the red one goes to the power supply. Which is this one, and here is the fuse. I could install the fuse with a small distance holder on the power supply board, so we have a fuse accessible parallel to the other fuses which are here. One of them is a 230 volt AC fuse. I think this is this one. A little bit, we have to be a little bit careful, but in general we have to unplug the unit when swapping fuses. Okay, that's it. Here we have the output of the, this is the output of the 13 volt, the red wire. Well, this is now done. Job is done, and next step is to check the correct operation, whether we really have 250 Hertz deviation with an input voltage of 2 volt RMS. This is a test setup for the measurement of the sensitivity of the FM modulation input. I need a new workbench. For this I need a new basement, and for this I need a new house, and for this I need a lot of money. Okay. What do we have here? Device under test. This is the input of the audio frequency generated here in this generator, set to 300 Hertz. In the moment it's in receive mode. That's a deviation meter connected to the antenna output. And here we have additionally a millivolt meter, which is connected to the voltage output of the generator to measure with high accuracy the RMS voltage, because I have here a problem. First, the meter here is not perfect. It's a rather, okay, it is calibrated but not perfect. And the next problem is I have an impedance of 200 ohms, series impedance, and here I have 1 kilo ohm input, so the voltage here measured it's on the side of the generator, it's a little bit higher, and the relation of 200 ohms to 1 kilo ohm. So this voltage indication here is obviously wrong for this input. In the moment I have set 1.4 millivolts. I can reduce it a little bit. 1.3 what I've calculated. Set the 145.0. Scope is connected to the output. It's just for indication that we have a sine wave. And now I go to transmit. But first I have to set the meter to noise cancelling. Without input voltage, the meter is set to 0. With the noise compensation, again, it is not a perfect compensation, but it's better than nothing. There's a filter, audio frequency broad and narrow, but this filter is not good for the purpose because it's a speech filter and it suppresses frequencies below 400 or 300 Hertz. So for the subtone, this filter is not optimized. I go to this point 300, 350. At the 300, I'm measuring 1.1 volt RMS. For 300 Hertz, 1.1 volt. You can see it here, RMS. That's what can be expected, and I will write it down. And now I will check it for other audio frequencies. I go back or down to 50 Hertz. I need a little bit more voltage. Now we have 300, 1.2 volt. When I increase the frequency up to 100 Hertz, I can reduce the amplitude a little bit. For 300 Hertz, again 1.1. So we have the range 1.1 volt over the whole subtone range between 50 Hertz and 250 Hertz. And now I'm measuring the same in the FM repeater operation. Up to now I've measured it without repeater operation for the 10.7 MHz FM oscillator. Now I switch over to repeater for the 10.1 MHz oscillator. Here I can measure with 1.1 volt RMS a little bit less, 250 Hertz. This is not exactly the same as before, but it's a minimum, some Hertz deviation, less deviation in FM repeater. I will try it again when I go down to 0, set with, okay, the noise cancelling is not perfect. Okay. Then I increase to 250, 300. Okay, it's 1.1. Same result as before. You see the noise figure is the problem of this little box. It's not perfect, but the values are nearly identical and can be accepted. This is a first test in my shack. The SE400 is connected on its rear side with the input of the subtone and is connected to the output of the generator, set to 123 Hertz. A little bit low, doesn't matter. 123 Hertz. Output voltage in the moment is 0, so we have no modulation. It is set to an UHF repeater very close to my location. We will see a very strong signal in the receive mode. I've set it to repeater mode. Here is only FM, not FM repeater. Repeater is made here in the transverter, the 7.6 MHz deviation. When I go to transmit without subtone, nothing happens. I have only weak output power. But when I increase here the input voltage, 1.3 volt RMS, test Delta Lima 7 Mike Alpha Juliet. Then we receive the repeater very strong, and then it switches off again. So we can see that the subtone operates. I reduce the amplitude down to less than 1 volt RMS. Again, test Delta Lima 7 Mike Alpha Juliet. We see the amplitude is not very important. Now we have, I go to 1 volt, 500 millivolt. Test, normal test, Delta Lima 7 Mike Alpha Juliet. Okay, we have seen that in the range of some 100 millivolt, 500 millivolt or so, it is sufficient. We do not need 1.1 volt RMS as calculated, can be less. Okay, a different repeater station may react differently, so this is not in general important. The frequency has to be rather correct. I've checked it because the distances from frequency to frequency is rather close, so the frequency has to meet within 2 or 3 hertz or so. Okay, that's it. That proves the concept that with such a generator we can operate with a subtone repeater, and now we have to replace this generator by a smaller subtone. Yes, I could work with this combination here, with this combo of course, but I don't like it. I need this generator in my lab, so I will replace it by a different type, and now we will see what we can do. We have seen in the last footage that it's possible to FM modulate the transceiver with a low frequency audio signal, as we have calculated. Now it's time to realize it. I bought such a small CTCSS encoder in the net for some euros, dollars, not so expensive. With this dip switches, it can be set to any frequency which is required. We have a pick on the rear side and some other components. There's an op amp for the output, and with this unit we can generate the frequencies. I need some additional components, an output amplifier, because the output is a little bit too weak for the low input impedance and for the voltage I need in the transceiver, and power supply, some switches, and so on. Here we have the setting of the dip switches and the wanted output frequency. I need these 4 frequencies, which I think for my region are optimum, and others can also be set, but I will do it a different way. I will use a switch with 4 positions, or yes, 4 positions, and use a diode matrix to program the inputs. That's possible. Another problem is that the output voltage is not constant. For higher frequencies the output voltage drops a little bit. This unit has a low pass filter in the output for a better sine wave, but this makes a difference between 1.07 volt RMS and 0.6 volt RMS unloaded output. So I need an amplification with an op amp to get a little bit more output voltage and especially a lower output impedance. This is my first design for the output driver for the subtone generator. That's the input. An amplification with an op amp. I use a standard op amp with a variable voltage gain with a switch with which I set the frequency. I will also vary the gain of the output. This is done with parallel resistors to this one. So for the higher frequencies where we have lower output, I will switch a resistor in parallel to this R2, and then therefore the loop gain is a little bit bigger, because the gain is determined by this resistor in relation to this one. This determines the gain. This is only for offset setting. I have only a unipolar voltage plus 9 volt to ground. I checked this circuit on an experimental board. It works. Here's the output. Voltage supply 9 volt, derived from 12 to 18 volt DC out of the transceiver. That's what I will realize now. These are the mechanical components, a small case, a profile. This is the front. I drilled in a hole for a switch. It's a 4-position switch with 2 levels. This is on-off switch. And the diode, which indicates when the generator is switched on. On the rear side we have the connector, 5-pole connector, and this is a small perforated board, experimental board. I cut exactly for this case. I can feed it in. Did I make it wrong? What did I do? Now it slides in. It slides in, it fits for the case here and the encoder and also the op amp. It's only a small integrated circuit. Can be placed here with some components. That's the output on this side, like this. Okay, some soldering. I do not create a board for it. Makes no sense. I will only produce one of these units and not more. And there are so many different versions which can be built, so I think a board makes no sense, so I don't do it. And please don't ask me for a board. I don't create a board. But I will show you the circuit, the drawing. This is a final schematic of the output driver. I reduced the pins to 1 here for the gain setting. It's not necessary to have 4 settings for the 4 frequencies. I can always choose 1 setting for 2 frequencies, so it is sufficient to have a little bit more rough setting of the output amplitude and not a very fine setting. It's not important, as we have seen, for the effect to have a variation of a maximum 10 or 15%. For the 2 low frequencies I can use 1 setting as this, and for the higher frequencies I will add a resistor in parallel, 200, 300 kilo ohm I have to check to get a constant output voltage for the higher frequencies. Power supply, I added a diode for reverse polarity. That's for the output driver. And that's for the setting of the output frequencies. On the board we have a dill switch, but I don't use it. I will use a rotary switch, a selector switch. In my case I use only 4 positions, and with diodes I'm pulling down the respective inputs of the peak to low with these diodes with the matrix. For 71.9 Hz I need these 4 diodes, and for the other frequencies I have chosen I need these diodes, so I can bypass the switch. The switch of course has to be set to off, otherwise we have an additional problem. Here I have added 4 resistors, pull-up resistors. I don't like when the diodes are not used to let it open, so I prefer a special resistor for pulling it up to 5 volt. So the cathodes are blocked because the inputs here have not a high current capability. So when the cathodes are open, there's some current flowing out, and I don't like this. Well, here I need only a 1-pole, 1 level 4 setting switch. Of course we can use only also a switch with 5, 6, 7 and more settings. No problem if you want to have more. I only need these 4 settings. Here we have the first test setup. That's the encoder. Here we have the parallel soldered wires to the diode matrix. This is a matrix with the diodes, the 4 settings. Here I will later connect the switch. Here we have the 4 pull-up resistors. As we have seen, this output part, op amp with some coupling capacitors. Here I will connect later the switch for the variable gain setting. Here we have the fine setting of the gain. This is a power supply, 9 volt, and this is input, the 5-pole DIN plug, which will be connected later to the transceiver. Here we have the plus pole coming from the transceiver. I have to connect it to the power switch on the front. This with this switch we have seen. This is the selector for the 4 frequencies, and here we have the PTT connection, which is connected to the output or to the input PTT input, which is here on the board. Okay, let's do a first test. I will connect a short test lead to simulate the switch on this side and here on this side. This is for the first frequency. This is that's 71.9. We can here read the frequency when I simulate it, shorting the PTT input. 71.9. Hope you can see it. I'll switch off the lamp. 71.9. The next frequency I choose. Next setting is 88.5. 88.5. Next one is 123. 123. And the last one, the fourth one, is 141.3. 41.3. And you'll see the difference in amplitude is not so big, only for the very low frequencies. There's a little bit more output voltage, so I will reduce it a little bit or increase the other ones by changing the parallel resistor for the negative feedback. Okay, the jack of the parallel resistor I need for the increase of the output voltage at high frequencies due to the low pass characteristic on the encoder. I found that roughly exactly 100 kilo ohm is the right one. For these two frequencies, 71.9 and 88.5, I have output voltage when I set this pot to the center of 1.0 and 0.88. It drops for higher frequencies down to this value, but with 100 kilo ohm in parallel, I have here again 1 volt and 0.86. So I have 1 volt, 0.88, 1 volt, 0.86. That's enough, so I can use this 100 kilo ohm in parallel with a switch, and that's the best solution. I do not need 4 settings, as we discussed. The wiring is nearly complete. The switch is wired. These blue lines are the diode matrix for the frequency setting. The 2 green ones is the amplification setting for the output level. These red ones is for the LED, and the switch also is not connected, so I connected the power supply directly to the input of this voltage stabilizer. Here we have ground, and this is a scope output, and now we can see whether it works, whether we can select rather easily the frequency, and whether the output level is nearly stable. The switch is set to the left position. This is a frequency of 71.9 Hertz. We can here read the frequency. The voltage RMS is difficult to read, but I will tell you what you should see. I simulate PTT. 71.9 as expected, and the RMS is something with 980, nearly 1 volt RMS. Next frequency, one step further, is 88.5. 890, 850 RMS. Next one is 123, 123. Output voltage again a little bit more than 1 volt RMS. And setting 4, 141.3 and 850. So the output voltage is stable between 850 millivolt and 1.1 volt RMS. That's more than sufficient for a constant deviation in the transceiver, so we can use it. And I will do the final wiring and then a first test with the transceiver. The wiring is complete. The unit is not in the case, but that's not important. First connection to the transceiver, a first test. The unit is switched on, but there is no subtone transmitted because the PTT is not activated. We are in the receive mode. And I see this in the output. Here the scope is connected. Frequency of 149 dot something kilohertz, 150 kilohertz. When I go to transmit, that's a subtone. Hope you can see it a little bit better. But without subtone, we still have an oscillation. What is the reason? The reason is a design problem. We have here in the output of the operational amplifier a rather high capacitive load. And op-amps do not like capacitive loads. We have no input from the encoder, from the subtone, but this op-amp is oscillating due to the capacitive load. And the capacitive load is made by this input circuit. We see here we have 10 nanofarad. Actually we have 3.9 nanofarad 2 times in parallel. So we have only 8 nanofarad, but that's not the question. We have here a rather high capacity. I've chosen this for filtering. But this is obviously a little bit too much capacitive load. So I have to think about it, what to do. Studying the manual of the TL081 series, I found that there are compensation capacitors proposed, and the TL081 has no direct connection for compensation, but I found by some experiments that the solution is to use a 100 picofarad capacitor, or a little bit less, between pin 6 output and pin 5. 5 is the compensation input, and obviously we can block the oscillation, but the signal, the subtone is not affected. I can show it. We have here the unwanted signal. I go to send, and when I add this capacitor in parallel, we have a clear signal, 123 Hertz, and full output. And without this capacitor, we have the oscillation. And I will add also a small resistor here in series to the output. I'm thinking about 50 ohms or so to reduce the capacitive load for the op-amp. I will do first also check this one and then add this 100 picofarad, irrespective whether this is effective or not. For a quick test, I added here a variable resistor, a trim pot 250 ohm in series. This is a setting of 0. We still have oscillations. But when I increase the resistance a little bit, we see it disappears. I estimate it's 10% or so of the full value of 250 ohms. So I think 50 ohms should be sufficient. And additionally, of course, I will add the 100 picofarad, as I've seen is also effective. I add it again. And when we go to transmit now, we have the output frequency, and when I reduce this resistor, we have the oscillation, and now the oscillation stops. I measure this resistor, take it 2 or 3 times and add it as a fixed value. And now both mods are made, 100 picofarad, and I measured 31 ohms. I've chosen 56 ohm in series. 56 ohm was sufficient to damp the oscillation, and additionally I added 100 picofarad here, so I think the circuit is now stable, also for changing load when using it with another transceiver. Okay, that's it. Now the circuit is, I hope, finally ready, and we can continue this project and finalize it. First I will bring the setting of the pot, of the output, to the right value, so that we have a frequency deviation in the range of 150 up to 200 Hertz. This will be the next step. Here we have the well-known test setup, deviation meter. The output is connected to the blue line, and the yellow line is the output of the encoder. When I switch on the encoder, I have to set it to 0, the compensation, okay, switch with the lowest frequency, which is 71.9 Hertz. It takes some seconds when the unit is switched on. Later, when we only use PTT, then it is stable. I can show it to you. I measure a deviation of 200 Hertz. I go to the next frequency. I have to switch off and switch on again. It's 88, also 200, 250 Hertz. Next frequency, 123 Hertz. A little bit more deviation. And then I go to the maximum frequency, which is 141.3. So we are always at 250 Hertz. That's okay. And now I can reduce the output power output voltage of the encoder a little bit. I will reduce it down to 600 to 800 RMS. This should be sufficient. Yes, 150, 200. Okay, but I want to show you simply the output of the encoder, which is constant, of course, when I go to receive mode. And then when I go to transmit, the signal is instantaneously present. Only the demodulator takes some time to stabilize. And now the task is to bring back this ready wired units into this case. It's a profile, cannot be opened. So you may ask, how is it possible? And no, I can confirm you, I'm not in the position of this fool. The reason is I have long wires and we can feed it through this way and then bring this unit into the slots, and then this unit in these slots. Then you see this unit comes out. Maybe I will fix the boards with some glue, but I think it's not necessary. And another item is the rubber. This is a profile side. I will slip it over like this. Can also be done. And here we have the profile side on this side. This is also a solution. The rest is bringing it into the right position and then use the 4 screws, and then the unit is ready. The case is ready. Some labels are missing. I will do it later. Transmitter is switched on, of course, with low power. The demodulator is synchronized, and when I switch on the subtone, we see a modulation deviation of 250 Hertz. A little bit more. Okay, I should compensate the noise better. Okay. Next frequency. A little bit much. Okay. Again, it's noisy, not so easy to read, but we have here 250 Hertz. Okay, the noise compensation is difficult. I have to install a new AF filter. Yes, 200, between 200 and 250 Hertz. That's 500 Hertz. That's okay. Now I will bring this unit into my shack and try to get access to the first repeaters. Now we are at the end of this project. The Subtone unit is connected to the transceiver. I placed it here for demonstration. Later I will place it on top of the transceiver. But just to demonstrate it, it's located here. It's switched off. When I go to send, nothing happens. And when I switch it on, go to send, the repeater answers. There is a signal. It works. Just to make it clear, we have a second knob here. It's call. This is a call for 1750 Hertz. This function is also still operating because this generator here is connected to the microphone amplifier, whereas this unit here is connected directly to the FM oscillator, to the 10.7 MHz. Of course, this tone call also modulates the 10.7 MHz oscillator, as we have seen in the videos. But these two units are completely separated from each other, and they can work independently, and they can still use the old call function. Conclusion, what can we say? Well, the modulation, the subtone modulation of an old transceiver is possible, but it's not so easy as you have seen. It depends upon the concept. In this case we were lucky because it's an all-mode transceiver and we have a separate 10.7 MHz oscillator. Others have 9 MHz oscillators for this purpose, to generate the FM, SSB and CW signal. If you have a pure FM transceiver, then it may be difficult because it has a PLL, and the oscillator, which is PLL locked, cannot be modulated with low frequencies, because the PLL is fast enough to work against the modulation, the low frequency modulation. So we would need a very low pass frequency in the PLL loop, and this makes the oscillator very slowly in regarding frequency changes. Not so easy. When we have a very old unit with crystals in it, channel crystals, then it is possible to modulate it with FM, as we have seen, because this is also a crystal oscillator which is modulated. But please be careful, some old transceivers have phase modulation, not frequency modulation. For example, the old ICAMs, as I know, have phase modulation, and the phase modulation with very low frequency, AF frequency modulation, generates nearly no deviation. That's a problem. Low frequency in phase modulation is not a solution. So not all old transceivers can be modified for subtone modulation in FM. That's the end of this project. A little bit funny, but it works now. Stay healthy, stay tuned. See you on this channel.